Welcome to RadOnc Smart Review Physics Edition.
Hello, everyone.
Today we are diving into what might be the single most critical aspect of safely delivering brachytherapy. We're talking about the essential quality assurance, the stringent safety protocols, and the fundamental regulations that govern its use in a clinical setting.
That's right. You know, when you think about radiation therapy, you often picture those large external beam machines, Linux, maybe CyberKnife, things like that.
Yeah, the big ones.
Exactly, where the radiation source is, many centimeters, sometimes even meters, away from the patient, and it's heavily shielded within the machine head and the thick concrete walls of the treatment room.
Right.
Brachytherapy is, well, it's fundamentally different.
It really is. Brachytherapy involves potent radioactive sources, typically iridium-192 for high dose rate, or HDR, maybe iodine-125, and palladium-103 for low dose rate, or LDR seeds. And these sources are placed inside or very close to the patient's tumor. You're not dealing with kilograms of lead shielding or tons of concrete like external beam.
No.
With brachytherapy, you or the equipment are potentially handling the source itself, or at least the applicator holding it much more directly.
And that proximity, right. Plus, the requirement for staff interaction with the source pathway, connecting guide tubes, loading applicators, and just the sheer high activity of HDR sources if something goes wrong.
Yeah.
It inherently escalates the potential risk significantly compared to external beam if any part of the QA or safety procedures breaks down. It's really not an exaggeration to say that meticulous QA and strict adherence to safety protocols are absolutely non-negotiable pillars.
Completely non-negotiable for ensuring both patient and staff safety, and also just keeping your facility legally compliant.
Absolutely. This isn't just about delivering dose accurately. It's about preventing potentially catastrophic accidents.
Definitely. And because of this unique risk profile, the source being right there, the guiding philosophy for minimizing radiation exposure to everyone's staff, patient's family, the general public, is the ALARA principle.
ALARA, as low as reasonably achievable. ALARA.
I guess.
It's really the core tenet of radiation safety. It means you don't just aim to stay below the legal dose limits. You actively work to keep doses as far below those limits as possible. You're constantly seeking ways to reduce exposure.
This is proactive.
Exactly. And the primary tools we rely on here are pretty simple concepts. Time minimizing the time spent near sources. Distance, maximizing your distance from sources. Always remember the inverse square law.
Right. Dose drops off fast with distance.
It really does. And shielding, using lead, tungsten, or other materials to absorb radiation when you have to be close or spend time nearby.
Okay, with that foundation set, let's maybe unpack the specifics. Starting with the rigorous quality assurance required for high-dose rate remote afterloader systems.
Okay, HDR systems. They're incredibly sophisticated machines, but they rely on a, relatively simple principle. You have a single, tiny, but extremely high activity iridium-192 source.
Very active.
Yeah, and it gets pushed out of its shielded safe by a wire drive mechanism, and it steps through programmed positions. We call these dwell positions in catheters or applicators that have been placed in or near the patient.
Okay.
But because that source activity is so high, errors can lead to significant dose misadministrations very, very quickly.
Makes sense. High rate means less time for error.
Precisely. If the source stays out longer than planned or goes to the wrong position, the dose gradient, the way the dose falls off, is so steep that the dose delivered to the tumor or nearby critical organs could be wildly off.
So this is why rigorous QA is just paramount here.
It's everything.
Let's talk about the source itself first.
Sure.
One of the most critical checks happens upon source exchange. This usually happens, every 3 to 4 months?
Yeah, about that. Because the iridium-192 isotope has a half-life of roughly 74 days, some either 3.8 days, technically. So its activity drops significantly over time.
So you need fresh ones periodically.
You do. And when a new source arrives, its strength must be independently verified by the facility.
And this isn't a job for just anyone, right? This has to be done by the facility's qualified medical physicist.
Absolutely. Must be a qualified medical physicist, or QMP. And critically, it has to be done before that source is allowed to be used for treating any patient.
Okay, so first thing before it goes live.
Think of it as the fundamental input check for your entire HDR brachytherapy program. Get this wrong, and everything downstream is affected.
So how is it done? What's the method?
The standard method involves using a calibrated well-type ionization chamber. It's basically a cylindrical chamber that the source is placed inside, and it measures the total radiation output. Crucially, the calibration of that well chamber must be traceable back to national standards. Usually, this happens through an accredited dosimetry calibration laboratory, or ADCL.
ADCL, got it.
These are specialized labs sanctioned by regulatory bodies, like the NRC or agreement states, to ensure their calibration equipment is spot-on accurate. It provides a chain of traceability all the way back to the primary standards laboratory, like NIST in the U.S.
Okay, so it's a validated measurement. What's the tolerance? How close does the measurement need to be to what the manufacturer says?
This is a key number. The regulatory tolerance for this initial source strength verification, the acceptance test, is that the measured air Kerma strength, which we usually call SK,
air Kerma strength.
must agree with the manufacturer's calibration certificate within a specific range, and that range is plus or minus 5%.
Okay, plus or minus 5%. That's a number you absolutely need to know cold for boards and practice.
Definitely. Now, some clinical sites might choose to implement a tighter internal tolerance, maybe plus or minus 3%, as part of their own, internal ALARA-driven QA program.
Going above and beyond.
Right. But the regulatory standard you absolutely must meet for accepting a new source is that plus or minus 5%. If your measurement falls outside that window, you cannot use that source clinically until the discrepancy is fully investigated and resolved.
Wow. So what happens if it's off? Why is that SK value so important?
Because SK is the fundamental input parameter into your dose calculations, specifically the Task Group 43 Dose Calculation Formalism, TG43.
TG43 vote.
That's the standard method we use in treatment planning systems to figure out the dose distribution around a brachytherapy source in water or tissue. If your measured SK that you put into the system is off by, say, 6%, then every single dose calculation you do for every patient using that source will also be off by 6%. It's a systemic error. It bypasses all the other checks downstream and directly impacts the dose the patient receives.
That makes perfect sense. Garbage in, garbage out, basically.
Exactly right.
Okay, so once the source is accepted, verified within plus or minus 5%, and loaded into the afterloader, the rigorous QA continues
Right.
on a daily basis.
Oh, yes. These are the daily QA checks. They're performed on every single treatment day before the first patient is treated. Non-negotiable.
Every single day. What do they cover?
They cover several critical functions designed to catch potential issues right before use. First up are the safety interlocks.
Okay, safety first.
Always. You systematically check the door interlock, arguably the most important safety feature. Does opening the treatment room door immediately retract the source and prevent beam on?
Critical check.
Absolutely. You verify the audio and visual monitors. Can you see and hear the patient clearly during treatment? Check the radiation room monitors. Do they alarm correctly if the source is exposed unexpectedly? Emergency off buttons, both inside and outside the room, must be checked to ensure they're accessible and functional. And crucially, the battery backup system needs verification. This is what retracts the source into its safe if the power fails during treatment.
Right. Can't have the source stuck out if the lights go out.
Missing a faulty door interlock seems like a textbook example of how a QA failure could lead to a really significant radiation exposure for staff.
It absolutely is. These interlocks aren't just minor checks. They are your primary lines of defense against accidental exposure.
Okay, what else is checked daily?
Another absolutely critical daily check is source position accuracy. This verifies that the radioactive source travels precisely to the programmed well positions within the applicator pathway.
How do you actually check that with such a tiny source moving inside a catheter? Well, common methods involve using radiographic film or something called an autoradiograph. You place the film under a special ruler or a jig that's aligned with a test applicator or guide tube connected to the afterloader.
Okay.
Then you program the source to go to specific known dwell positions, expose the film briefly at each spot, and then develop it. You then measure the location of the dark spots, the source images on the film, relative to the markers on the jig or ruler to verify the source's position accuracy.
So you're taking a picture of where the source stopped.
Essentially, yes. Some modern systems also have integrated electronic position verification systems that can do this check automatically, which is nice.
And the tolerance for this daily check is incredibly tight, too, which really speaks to its importance.
It is astonishingly tight. The tolerance for daily source position accuracy for an HDR acroloader is less than or equal to plus or minus 1 millimeter.
1 millimeter. Plus or minus 1 millimeter. That's about the thickness of a credit card.
It is.
That feels incredibly precise for a machine moving a source on a wire.
You mentioned steep dose gradients earlier. What does being off by even, say, 2 millimeters actually mean clinically?
It means everything. The dose drops off incredibly rapidly around a brachytherapy source. Close to the source, the dose can decrease by 10, 20, even 30% or more for every millimeter you move away.
Wow.
So imagine you're treating, say, a cervical cancer patient, and you're trying to deliver a very high dose right to the tumor surface, which might only be a few millimeters away from the rectum or bladder.
Very close critical structures.
Exactly. If your source is programmed to dwell at a specific point to deliver the prescribed tumor dose while sparing that organ, and its actual position is off by just 2 millimeters, you could drastically underdose the edge of the tumor and significantly overdose the adjacent critical organ at the same time.
A double whammy. Precisely. That plus or minus 1 millimeter tolerance isn't arbitrary. It's absolutely necessary to ensure the intended dose distribution with those incredibly steep gradients is actually achieved in the patient. It's like, you're needing surgical precision, but with radiation dose delivery.
That's a great analogy, surgical precision. Okay, so daily checks include interlocks and positional accuracy within plus or minus 1 millimeter. What else?
You also check timer accuracy and what's called the end effect.
Timer accuracy seems obvious, but end effect.
Yeah. Timer accuracy is checking that the machine delivers the programmed dwell time accurately at each position. The end effect, sometimes called transit dose, refers to the dose delivered while the source is traveling between door positions or from its safe to the first position and back.
Ah, so it's not instantaneous teleportation?
Chuckles. No, unfortunately not. The source is emitting radiation during that transit time. The system must correctly account for this distributed dose or ensure the dwell timer calculation compensates for it accurately. So you perform checks to ensure the timer is linear, meaning 2 seconds is twice as long as 1 second, and accurate across different treatment times and numbers of dwell positions.
Okay. And console functions.
Also part of the daily routine. You just verify that the control console communicates properly with the afterloader unit itself, that all the displayed parameters like the programmed dwell times and positions are correct on the screen, and that essential functions like the printer, which generates the official treatment record, are working properly.
I have the paperwork.
Absolutely. And finally, after you perform a test run, you usually run a short dummy treatment plan to check the source extension and retraction. You perform a radiation survey of the treatment room.
With a survey meter.
Yes, using a calibrated survey meter. You walk around the room to confirm that the source has retracted fully back into its shielded container within the afterloader unit, and that the radiation levels in the room have returned to background levels. This is your final, all-clear check before a patient enters the room.
So that's the daily grind for HDR QA. What about less frequent but maybe more comprehensive QA?
Right. That falls under monthly, quarterly, or annual QA, depending on the specific check and your facility's license or regulatory requirements. These checks go deeper than the daily routine.
Okay. Like what?
You'll perform a more detailed verification of positional accuracy, often testing the source's movement over the full length of its possible travel in the guide tubes, not just a few points. You'll do more extensive checks of timer linearity and overall accuracy across a wider range of times.
More thorough.
Exactly. A crucial check here is verifying that the decay calculations used by your treatment planning system, the TPS, perfectly match the calculation the afterloader machine uses internally. This ensures that as the source activity decreases day by day over its lifespan, the system accurately adjusts the dwell times to deliver the correct prescribed dose.
Ah, so the planner and the machine agree on the source strength today.
Precisely. You'll also retest the full functionality of all the interlocks and safety features, not just the subset check daily, really put them through their paces. And you perform constancy checks on the specific electrometer and well chamber that you use for your source calibration measurements, just to make sure your measurement equipment itself hasn't drifted over time.
Checking the checker.
Exactly. And a very important component of these less frequent checks is conducting practice drills of your emergency procedures.
Wow, the drills.
Yeah, because if a real emergency happens, like a stuck source staff need to react automatically, correctly, and calmly under intense pressure, practice makes perfect, or at least makes the response much safer.
It definitely sounds like a layered approach. Frequent quick checks backed up by less frequent, more detailed testing, defense in depth.
That's a good way to put it. It's about building redundancy into the safety system. Now, shall we pivot slightly to low-dose rates, source quality assurance and handling?
LDR.
Yeah, let's do LDR. This involves discrete individual radioactive sources, right? Like seeds for prostate implants, or maybe needles and tubes for temporary implants. Different ballgame than the HDR afterloader.
Completely different QA and handling needs. For LDR sources, the QA really starts the moment they arrive at your facility. The very first step is verifying the source identity and strength. Meaning you need to confirm you received the correct isotope iodine-125, palladium-103, cesium-171, whatever you ordered, and that the activity or air Kerma strength matches what you ordered and what the manufacturer's calibration certificate says.
How you do that for, say, 100 tiny seeds? Well, you don't measure every single one individually, usually. You typically assay a representative sample of the shipment. For example, if you receive a large batch of prostate seeds loaded in sterile needles or stranded in ribbons, you might take a few seeds from different needles or ribbons, maybe 5 or 10% of the batch, and measure their individual air Kerma strength using your calibrated well chamber.
Okay, sample check.
Yeah, you verify the average strength and the consistency across the batch against the certificate.
You also perform a basic number and uniformity check.
Right, absolutely. This involves carefully counting all the sources received to ensure the number matches the packing list. Sounds simple, but you'd be surprised. And you visually inspect them, usually under appropriate shielding and magnification, to check for any obvious damage or defects in the source encapsulation. You don't want to implant a damaged seed.
No, definitely not.
No.
And the facility physicist does a calibration verification.
Yes, based on their sample assay measurements. While the manufacturer provides a calibration certificate, the facility must independently verify it. The acceptance tolerances for LDR sources might sometimes be slightly wider than that strict 5% for HDR source acceptance, perhaps ranging from plus or minus 5% up to maybe plus or minus 10%, depending on the source type and specific regulatory or institutional policy. But you still have to verify it.
Okay. Now, unlike an HDR source, which is mostly fixed inside the afterloader, these LDR sources are physically transported, stored, handled individually or in small groups. That makes inventory and security super important, I imagine.
Paramount. Absolutely mandatory. You must maintain strict cradle-to-grave tracking of every single source.
Cradle to grave.
From the moment it's received, through its use in a patient, if temporary, or tracking its location, if permanent, back into storage, if applicable, and finally documenting its decay in storage or transfer for authorized disposal.
Wow, detailed tracking.
Every single source. And LDR sources must be kept in a secure, locked storage location, usually a shielded safe or a designated locked room to prevent loss, theft, or unauthorized access. Regular physical inventory checks are also required, maybe quarterly, where you literally count or verify the presence of every single source listed in your inventory records to ensure nothing has gone missing. A lost LDR source is a very serious regulatory event.
I can imagine. Okay, speaking of source integrity and preventing problems, let's talk about sealed source leak testing, commonly known as wipe tests. This seems fundamental.
It is fundamental, and it applies to a model sealed radioactive sources used in brachytherapy.
All sealed sources. That's a key point.
Yeah.
So the high-activity HDR iridium source,
Yes.
individual LDR seeds, needles, tubes,
Yes.
even things like cobalt eye plaques with sealed sources.
If it's a sealed radioactive source intended for medical use, it has to be leak tested according to regulations.
And the purpose is pretty straightforward, right? Just making sure nothing's leaking out.
Exactly. To ensure that radioactive material is not escaping from the sealed encapsulation of the source. If that seal is broken or compromised, the radioactive material inside could leak out. That could contaminate surfaces, potentially expose staff who handle it unknowingly, or even contaminate the patient if it's an implant.
That sounds like a major hazard, a contamination and exposure nightmare.
It absolutely is, which is why the testing frequency is mandated.
Okay, so what is the required frequency for these wipe tests?
They are required before the first clinical use of any source. So when a new HDR source arrives from the manufacturer, or when you receive a new batch or vial of LDR seeds, you perform a wipe test before they are used on a patient.
First use check? And after that?
After that initial test, they are typically required every 6 months, periodically. Additionally, you must perform a wipe test anytime you suspect a source might be damaged, for instance, if an HDR source gets jammed, or an LDR seed is dropped, or if its physical appearance looks unusual.
Okay, every 6 months routinely. Plus, if damage is suspected. How is the test actually performed? What do you do?
You take a small piece of filter paper, or maybe a cotton swab. Sometimes it's slightly dampened with an appropriate solvent like ethanol or water, though often a dry wipe is sufficient and preferred to avoid damaging the source. You then physically wipe the surface of the source itself, if accessible and safe, like the outer capsule of an HDR source during exchange. Or, more commonly, you wipe its container, transport shield, or the immediate storage area where any loose contamination might accumulate.
So you're trying to pick up anything that might have leaked out.
Exactly. The goal is to pick up any removable radioactive material. Then you take that filter paper or swab and you measure the amount of radioactivity on it using a very sensitive radiation detector.
Like what kind of detector? Needs to be sensitive, you said.
Usually a well-type scintillation counter, like a sodium iodide well counter, or sometimes a liquid scintillation counter for even higher sensitivity, especially for low-energy beta emitters if those were being tested, though most brachy sources are gamma or X-ray emitters suitable for a well counter. The key is the detector needs to be sensitive enough to detect extremely low levels of activity, far below what would cause a hazard immediately, but enough to indicate a potential leak.
Okay, and what's the critical limit? What amount of removable contamination means the source is officially considered leaking according to regulations?
This is another number to burn into your memory. The limit is that the removable contamination must be less than 0.005 microcuries.
Less than 0.005 microcuries. That sounds incredibly small.
It is very small. To give you the equivalent in SI units, that's 185 becquerels BQ.
Okay, less than 0.005 microcuries or 185 becquerels. So if your wipe test measures activity equal to or greater than that limit,
Then the source is considered leaking.
and if a source is found to be leaking, what happens then?
The action is immediate and serious. That source must be removed from service right away. No questions asked. It needs to be contained properly, often double-bagged in plastic, or placed in a sealed container to prevent any further spread of contamination.
Okay.
And the event must be reported according to regulatory requirements. This usually means immediately notifying the facility's radiation safety officer, the RSO.
RSO, got it.
And depending on the source activity and specific state or NRC regulations, it might also require prompt reporting to the regulatory agency itself. A leaking source is a significant regulatory incident and requires careful management and investigation.
This really underscores why those routine 6-month wipe tests and the initial acceptance test are so vital. They're designed to catch this kind of source integrity failure before it causes a major contamination event or unnecessarily exposes staff or patients.
Absolutely. It's a critical preventative measure.
Agreed.
Yeah.
Okay, moving on. Performing radiation surveys using a calibrated survey meter seems like another fundamental activity throughout all brachytherapy procedures and also for patient release.
Fundamental. You need to know where the radiation is and how much there is.
What types of survey meters are typically used in brachytherapy?
Well, there are two main types you'll encounter. For detecting very low levels of radiation, like searching for a lost LDR seed or checking for minor contamination, a Geiger-Müller counter. A GM counter is often preferred because of its high sensitivity. It clicks audibly even for low count rates.
The classic clicking detector.
That's the one. However, for accurately measuring dose rates, say, the radiation level at 1 meter from a patient with a permanent implant, or checking the radiation levels outside a shielded treatment room, an ion chamber-based survey meter is more appropriate.
Why the ion chamber for dose rate?
Because ion chambers provide a reading that is much more directly proportional to the actual radiation dose rate, like milliroentgen per hour or microsievert per hour, and they are less affected by high count rates or the energy of the radiation compared to a GM counter. GMs can saturate or give misleading readings at higher dose rates or for different isotopes if not specifically calibrated.
Okay, so GM for detecting small amounts or confirming absence. Ion chamber for accurately measuring dose rates. Makes sense. When are these surveys typically performed?
Lots of times. After every single HDR treatment, you must survey both the patient, usually near the applicator site, and the entire treatment room.
Why both?
This confirms two things. One, that the source has fully retracted back into the afterloader's shielded safe, and two, that there are no unexpected radiation levels remaining in the room, basically confirming the source is truly shielded and safe. The patient themselves should have essentially zero radiation output after the source is retracted.
Okay. What about LDR?
Similarly, after the removal of a temporary LDR implant, think about removing gynecological tandem and ovoids or interstitial needles after a few days. A thorough survey is absolutely mandatory.
What do you survey them?
You survey the patient carefully at the implant site. You survey any dressings or bandages removed. You survey the bed linens. You survey the trash. And you survey the entire room.
Wow, everything.
Everything. This is a critical step to ensure all the radioactive sources have been successfully removed and accounted for. None must be accidentally left behind in the patient or lost in the linens or trash. A retained source is a very severe medical event and a major regulatory violation.
I can see why the thorough survey is needed there. And then for permanent LDR implants, like prostate seeds.
For permanent implants, you survey the patient before they are released from the facility. This survey typically measures the dose rate from the patient at a specific distance, very commonly at 1 meter.
Why 1 meter?
It's a standard distance used for radiation protection calculations and regulatory limits. The result of this 1 meter survey helps determine if the patient meets the criteria for being safely released into the public.
Which brings us neatly to the specific patient release criteria, particularly under the U.S. Nuclear Regulatory Commission, or NRC regulations. What's the rule?
The fundamental rule, and this comes directly from the regulations, specifically 10 CFR Part 35.75 for medical use.
10 CFR 35.75.
Okay. The rule states that a patient who has received radioactive material, like a permanent implant, can be released from the facility if the calculated total effective dose equivalent, or TEDE, to any other individual from exposure to that patient is unlikely to exceed 5 millisieverts.
5 millisieverts, TEDE, TEEDE. Okay, what's the equivalent in the older unit, rem?
5 millisieverts is equal to 0.5 rem. So the core regulatory requirement is ensuring that the anticipated dose to anyone else, family member, coworker, member of the public, who might interact with the patient after release, should not exceed 5 millisieverts over the entire duration of their exposure to the patient.
What exactly is TEDE?
TEDE, total effective dose equivalent, is a concept used in radiation protection to try and quantify the overall risk. It sums up the dose received by the whole body from external radiation exposure, plus the dose received from any radioactive material taken into the body, internal exposure. Now, for a patient with a sealed implant like prostate seeds, it's primarily the external dose component that's relevant for exposure to other people.
Okay, so 5 millisieverts TEDE to others is the actual regulatory limit. But you mentioned we measured the dose rate at 1 meter. How does that relate? We're not usually calculating a full TEDE for every potential contact person before releasing a prostate seed patient, right?
That's correct. Doing a full TEDE calculation for every possible scenario would be incredibly complex and impractical. So the dose rate measured at a specific distance, like 1 meter, is used as a practical surrogate or a screening tool.
The surrogate, okay.
The idea is that if the dose rate at 1 meter is below a certain level, it provides confidence that the fundamental 5 millisievert TEDE limit to others is unlikely to be exceeded under reasonably foreseeable circumstances.
What's that dose rate level typically? Well,
the NRC provides guidance. For example, releasing a patient with a permanent implant is generally considered acceptable if the measured dose rate is less than 0.05 millisievert per hour at 1 meter. There are also activity-based limits in the regulation, like releasing someone if they have less than 30 millicuries of iodine-125 remaining.
Okay, so maybe less than 0.05 millitiovert at 1 meter.
Or similar levels, yes. The key takeaway is this. While measuring the dose rate at 1 meter is a common and important clinical practice for release, you need to understand that the fundamental regulatory requirement you are actually meeting is the 5 millisievert TEDE to others limit. The dose rate measurement is how you demonstrate compliance with that underlying rule.
Got it. The dose rate at 1 meter is the practical way to show you're meeting the 5 millisievert TEDE criterion. And importantly, for any patient released with a radioactive implant, regardless of the type or dose rate, they must receive written instructions. Correct.
Absolutely mandatory, written instructions. These are crucial for the patient and their family. They provide clear, understandable advice on how to minimize radiation exposure to other people.
What kind of advice?
Things like maintaining a certain distance from others, especially vulnerable individuals like children and pregnant women, limiting the duration of close contact, like huddling or prolonged sitting together. Sometimes specific advice on sleeping arrangements for a certain period.
Practical stuff.
Very practical. This empowers the patient to actively participate in adhering to the ALARA principle after they leave the controlled environment of the hospital or clinic.
Makes sense. Okay, let's shift gears slightly to talk about safety procedures and emergency response. Given the potential hazards we've discussed, having robust, well-documented, and regularly practiced procedures seems absolutely paramount in brachytherapy.
Paramount is the right word. You have to be prepared.
Let's start with some basic principles for source handling, especially relevant for LDR or manual loading procedures.
Rule number 1, always worth repeating. Always use tools. Forceps, transfer devices, shielded containers, guide tubes. Never, ever handle radioactive sources directly with your fingers or hands.
Okay, rule #1. Tools, not hands.
Rule #2. Maintain distance whenever possible. Remember that inverse square law, doubling your distance cuts the dose rate down by a factor of 4. Use long-handled forceps. Stand back when you don't need to be close.
Rule #2. Distance is your friend.
Rule #3. Minimize time. Work efficiently, but safely. Plan your actions before you handle the source so you're not fumbling around near it. Minimize the time you spend in close proximity. Time, distance, shielding the pillars of LARA.
Rule #3. Be quick, but careful. Time, distance, shielding,
Got it.
and using portable shields.
Yes, use portable shields like L-block shields on a benchtop or rolling shields whenever they are available and appropriate for the task you're performing. But honestly, that first rule is the most fundamental and sometimes the easiest to forget in a rush. Never handle radioactive sources directly with your hands. It's the easiest way to get a very high radiation dose to your extremities or potentially spread contamination if the source integrity is compromised.
Okay, what about the treatment room environment itself? What are the key safety requirements there, especially for HDR?
The room itself needs proper structural shielding, concrete, lead steel designed by a qualified expert to ensure radiation levels in adjacent occupied areas like offices, waiting rooms, corridors are well below regulatory limits when the source is exposed.
Shielding? What else?
Warning lights outside the room are mandatory. They must clearly indicate when a source is exposed inside, usually a red light saying radiation on or source exposed.
Visual warning.
And those door interlocks we talked about for HDR are absolutely essential. They must automatically retract the source or prevent DMON if the door is open during treatment delivery.
Interlocks. Critical.
Viewing systems, typically closed-circuit TV cameras and two-way audio communication systems, are also required. This allows staff to constantly monitor the patient's condition and communicate with them during treatment without having to be physically present in the room, reducing staff exposure during BMON to 0.
Makes sense. Video and audio links.
And finally, clearly accessible emergency off buttons or emergency source retract buttons must be located both inside the treatment room, near the patient, and outside at the control console. These provide a quick way to stop the treatment and retract the source in an emergency.
Okay, multiple layers of safety built into the room. Now, what about potential emergencies? Things going wrong. What are the key scenarios staff need to be trained and prepared for, and why are those practice drills you mentioned earlier so important?
Facilities must have detailed, written, documented procedures for various potential emergency situations. And staff need to conduct periodic drills, actually walk through the steps to ensure they know exactly what to do under pressure when instinct takes over.
What's the most commonly discussed HDR emergency scenario?
Probably the stuck or disconnected source. What happens if the HDR source fails to retract automatically at the end of the treatment or gets disconnected from the drive wire inside the patient?
Okay, that sounds serious. What are the immediate first steps? You mentioned a mnemonic earlier, CSN.
Yes, CSN is a good way to remember the initial response. C is for console.
Console.
The immediate first action is always to attempt an emergency source retract using the dedicated buttons or functions on the treatment control console. Try the remote option first. It's the safest and easiest way to try and regain control and get the source back into its shield. If that works, great. You verify the source position using the room monitor or a survey meter, and then proceed according to your facility's protocol.
Okay, try the button first, if that doesn't work.
Then S is for secure. You must secure the treatment room immediately. This means ensuring the door is closed and locked, or at least guarded, to prevent anyone from inadvertently entering the room while the source is still exposed.
Keep people out. What about the patient?
The decision on whether to keep the patient in the room or attempt to safely remove them depends heavily on the specific situation, like where the source is stuck, the patient's condition, and critically, on the pre-approved institutional emergency procedure. Removing the patient with the source potentially still attached or nearby carries its own risks. This is a decision that needs to be made rapidly by the authorized user physician and qualified medical physicist based on the specifics and their practice plan.
Okay, so secure the room, assess the patient situation based on protocol, then what?
Then N is for notify. Immediately notify the qualified medical physicist and the authorized user physician. These are the designated experts who will take charge. They'll assess the situation, potentially use survey meters to estimate dose rates, determine the safest course of action, and if necessary, guide or perform the manual source retraction procedures.
Manual retraction. That sounds tricky.
It is. Manual retraction is a complex, potentially high-exposure task that should only be performed by trained individuals following strict, pre-practiced protocols, using specialized tools and portable shielding. It's a last resort, but you have to be prepared for it.
So CSN console, secure, notify. That breaks down the initial response nicely for a stuck HDR source.
What about a lost source scenario? Maybe more likely with LDR seeds.
A lost source event is equally serious, though different. If you realize during LDR handling, implantation, removal of a temporary implant, or even during routine inventory that a source is missing, the first rule is all work in that area stops immediately.
Stop everything. Don't keep going.
Exactly. Do not proceed with anything else until the source situation is addressed. Then you systematically survey the entire area where the source could possibly be located. Use an appropriate, sensitive survey meter, like a GM counter, and be methodical. Check floors, trash cans, linens, equipment.
Okay, stop then survey. Then secure the suspected area, rope it off, put up signs, prevent anyone from walking through it, potentially stepping on the source, moving it, or unknowingly being exposed. And finally, immediately notify the radiation safety officer, the RSO.
Notify the RSO again.
The RSO is the designated person responsible for directing the search, coordinating efforts, performing necessary dose assessments if someone might have been exposed, and managing the source recovery and all the required regulatory reporting.
Got it. Stop, survey, secure area, notify RSO for a lost source. Are there other emergency procedures needed?
Yes, facilities also need procedures for dealing with patient medical emergencies that might happen during a brachytherapy treatment. These procedures need to integrate radiation safety protocols, for example, how to safely get emergency medical staff, like a code team, into the room if the HDR source is out. Usually this involves performing an emergency source retract first, if possible.
Right. Protect the responders, too.
Absolutely. And the personnel involved in brachytherapy are key to safety. The roles of the authorized user physician, who is responsible for the prescription, overseeing the treatment and overall patient care, and the qualified medical physicist responsible for all the QA, calibration, treatment planning, physics support, and physics input during emergencies are absolutely critical, particularly in HDR and complex LDR procedures. And it's not just them. All staff involved in brachytherapy, nurses, radiation therapists, dosimetrists, physicists, physicians, must have specific documented radiation safety training that is tailored to their roles and responsibilities in handling or working near radioactive materials.
Okay, so let's try to zoom back out now. We've covered a huge amount of ground, from daily HDR checks and source calibration to wipe tests, surveys, release criteria, and emergency drills. Why does all this meticulous QA, all these safety procedures, and strict regulatory compliance really matter in the grand scheme of things? What's the bottom line?
Well, it matters because the stakes are incredibly high in brachytherapy. First and foremost, it's about preventing errors. Every single QA check we discussed is a potential safeguard, a layer of defense designed to catch a problem before it leads to a patient mistreatment or an unnecessary staff overexposure.
Like catching a faulty interlock before someone walks in.
Exactly. Or catching a positional error exceeding that crucial plus or minus 1 millimeter tolerance before the wrong dose distribution is delivered. Or finding a miscalculated source decay correction before multiple patients are treated with the wrong activity. Any of these failures can directly result in the wrong dose being delivered or an unintended, potentially harmful exposure.
You know, that plus or minus 1 millimeter HDR position tolerance really stands out. It's not just some engineering specification you check off on a form, is it?
Not at all. It's literally the difference between delivering the intended high dose precisely to a small tumor target and either missing part of that target or delivering a dangerously high dose to a nearby healthy organ simply because of how incredibly fast the dose falls off with distance. Ignoring that tolerance fundamentally compromises treatment accuracy and patient safety.
Right. Okay, so preventing errors is number one. What else?
Secondly, it's about ensuring dose accuracy. That initial source strength verification, remember the plus or minus 5% tech upon receipt, and ensuring accurate timer functionality are what guarantee that the dose calculated in the treatment planning system is the dose actually delivered to the patient. You can have the most beautiful, perfect treatment plan, but if your input source strength or your machine's dwell times are significantly off, the patient simply isn't getting the dose the physician prescribed.
Makes sense. Ensuring the planned dose equals the delivered dose.
Third, there's patient safety beyond just the dose accuracy and also public safety. Performing those thorough post-treatment surveys, rigorously meeting the patient release criteria that 5 millisievert TEDE limit to others, and providing those clear written instructions are what protect the patient once they leave the facility and, just as importantly, protect their family and the general public from unintended or excessive radiation exposure.
Protecting others is key.
And fourth, staff safety is paramount. Using remote afterloaders for HDR significantly reduces staff dose compared to historical manual techniques. Implementing proper structural and portable shielding, consistently using appropriate handling tools instead of hands, wearing personal radiation monitoring devices like TLDs or OSL dosimeters, and strictly adhering to practiced safe handling techniques. These all work together synergistically to minimize occupational radiation exposure, truly embodying the ALARA principle in daily practice.
Keeping the team safe.
And finally, let's not forget regulatory compliance. Adhering to NRC or state-specific regulations regarding facility licensing, source security protocols, mandated testing frequencies like those 6-month wipe tests, maintaining meticulous records and reporting incidents when required isn't optional. It's a legal requirement to operate.
It's the law.
It's the law. Failure to comply can lead to significant consequences. Warning letters, hefty fines, mandated shutdowns for retraining, loss of license, or even the complete closure of a brachytherapy program. So it's not just about good practice. It's about maintaining your legal right to perform these treatments.
Okay, that really covers the why it matters. Let's maybe try to distill some of these absolutely critical points into must-remember items, maybe perfect for reviewing for boards or just keeping sharp in the clinic.
Sounds like a good idea. A quick review.
Okay. For HDR QA, daily source position checks must be within plus or minus 1 millimeter. The acceptance tolerance for source calibration upon receipt is plus or minus 5% compared to the vendor's certificate. And mandatory daily checks include verifying safety interlocks, timer accuracy, and the functionality of the emergency source retract mechanism. Anything else for HDR?
Those are the big daily acceptance ones. Remember the less frequent checks too, like TPS decay, calculation verification, and full interlock tests?
Right, for LDR QA and handling. Key elements include independent source assay, or counting upon receipt, maintaining a strict auditable inventory of every single source, cradle to grave, and ensuring secure, locked storage at all times.
Absolutely. Don't lose those seeds.
Wipe tests. Mandatory every 6 months for all sealed sources and also upon receipt of any new source. The critical limit for removable contamination that indicates a leak is less than 0.005 microcuries, which is the same as 185 becquerels. Remember that number?
Less than 0.005 microcuries, 185 becquerels.
Got it. Patient release criteria. The fundamental NRC rule is that the total effective dose equivalent, TEDE, to any other individual from exposure to the patient must be unlikely to exceed 5 millisieverts, or 0.5 rem. This requires a survey of the patient before release and providing clear written instructions to minimize exposure to others.
5 millisieverts TEDE to others. That's the core.
Emergency procedures. You absolutely must know the documented basic steps for dealing with the most likely emergencies. For a stuck HDR source, remember CSN console, secure, notify. For a lost LDR source, stop, survey, secure area, notify RSO. Regular practice drills of these procedures are required.
Know your emergency plan. Practice your emergency plan.
And finally, the standard strength specifier for modern brachytherapy sources, the quantity you use for dose calculations in TG43.
That would be air Kerma strength, universally abbreviated as SK.
SK. Excellent review. All right, let's see if that's stuck in it. Time for a quick board review blitz. 4 questions, styled like you might see on an exam. Ready?
Let's do it. Bring it on.
Question number 1. What is the primary reason for performing frequent wipe tests on sealed brachytherapy sources? Is it A, to verify the air Kerma strength of the source for treatment planning, B, to ensure the source position accuracy within the afterloader, C, to detect any leakage of radioactive material from the source capsule, or D, to clean the source surface for better dosimetric accuracy?
Okay, primary reason for wipe tests. We just covered this. It's all about checking the integrity of the source seal. So the answer has to be C, to detect any leakage of radioactive material from the source capsule.
Correct. Answer is C. Wipe tests are specifically for leak detection. Question number 2. According to typical regulatory guidelines and standard clinical practice, what is the required tolerance for daily source positioning accuracy checks for a high dose rate HDR remote afterloader? Is it A, plus or minus 0.1 millimeters, B, plus or minus 1 millimeter, C, plus or minus 2 millimeter, or D, plus or minus 5 millimeters?
Okay, daily HDR position check. We emphasize how tight this is because of the dose gradients. It's that credit card thickness. Answer B, plus or minus 1 millimeter.
You got it. Plus or minus 1 millimeter. Answer is B. Question number 3. For permanent LDR seed implant release in the U.S., the primary NRC criterion for releasing a patient into the public is that A. The measured dose rate at 1 meter from the patient must be less than 0.02 millisievert per hour. B. The total activity remaining in the patient must be less than 1 millicurie. C. The calculated total effective dose equivalent, TEDE, to any other individual from exposure to the patient is unlikely to exceed 5 millisieverts. Or D. The patient must wait a time period equal to 1 effective half-life of the implanted isotope before release.
Right, we talked about how A and B might be practical surrogates or guidance levels, but the fundamental regulatory basis, the actual rule in 10 CFR 35.75, is about the dose to others. So the answer is C. The calculated TEDE to any other individual is unlikely to exceed 5 millisieverts.
Excellent. That's the core requirement. Answer is C. Final blitz question number 4. In the event that a high dose rate HDR source fails to retract automatically at the end of a treatment, what are the immediate first steps according to typical emergency procedures? Is it A. Immediately enter the room to manually retract the source using forceps. B. Call the radiation safety officer and wait outside the room for further instructions. C. Instruct the patient to exit the room as quickly as possible while keeping the door open. Or D. Attempt an emergency source retract using the console buttons, secure the room by closing the door if safe and appropriate based on protocol, and immediately notify physics and physician personnel.
Okay, stuck HDR source. Immediate first steps. Remember, CSN console first, then secure, then notify. Option A is dangerous and not the first step. Option B skips trying the console. Option C could be dangerous depending on the situation. Option D matches CSN perfectly. Attempt console retract, secure the room, notify the expert. So D is the answer.
Nailed it. Answer is D. You're definitely ready for that part of the physics boards. Now let's move to some clinical pearls. These are practical, high-yield takeaways to really carry with you into daily practice.
Okay, pearls of wisdom. Let's hear them.
Pearl number 1. That plus or minus 1 millimeter daily HDR position tolerance. Don't ever think of it as just a number on a checklist. Internalize why it's so tight. It's the practical implementation of needing near-surgical accuracy in placing that intensely radioactive source because the dose falls off so incredibly fast nearby. Being off by more than a millimeter means your carefully planned dose distribution is almost certainly not what the physician prescribed or intended for the patient's anatomy.
Pearl number 2. Engrave this magic number for wipe tests into your brain. Less than 0.005 microcuries, or 185 becquerels, of removable contamination is the limit. If you wipe a source or its container or stored spot and your measurement shows activity equal to or greater than that tiny amount, the source is officially leaking. Stop everything immediately, contain it safely, and report it through the proper channels, RSO, physician. It's a significant event requiring immediate action.
Pearl number 3. Patient release after a permanent implant like prostate seeds isn't determined by the dose rate at 1 meter needing to be 0 or background level. That's often impossible right after implant. It's fundamentally about ensuring the calculated total effective dose equivalent, TEDE, to any other individual is unlikely to exceed 5 millisieverts. Use the measured dose rate at 1 meter for your checking if it's below 0.05 millis/VHR as your practical screening tool to demonstrate compliance with that TEDE limit. And always, always provide clear, simple written instructions to the patient on how they can minimize exposure to their loved ones.
Pearl number 4. ALARA isn't just an acronym you learned for the boards. It's truly a way of life in brachytherapy safety. When handling any source or working near an exposed source, constantly think time, distance, shielding. Always use appropriate tools, forceps applicators. Maximize your distance whenever feasible. Work efficiently but carefully to minimize exposure time. Use shielding when appropriate. And never ever touch sources directly with your hands. It's how you protect yourself and your colleagues day in and day out.
Speaking of boards, it's kind of funny, isn't it? You spend months, maybe years, cramming all these incredibly detailed physics principles, equations, and numbers.
Yeah, yeah.
Chuckles. And then the day after you pass the exam, it feels like some of the really specific stuff just poof,
Yeah.
it evaporates from your brain.
Laps, absolutely. You're thinking inverse square law. Yeah, I know that one. Dose goes down as you get further away. Wait, was it the square of the distance? Or maybe it was cubed in tissue. Whatever. It goes down, right? Close enough.
Laughs.
Yeah.
Exactly. Been there. It's true. The sheer volume of physics required for radiation oncology boards can be absolutely overwhelming. But the core concepts, especially for these high-risk modalities like HDR and LDR brachytherapy, are the ones that absolutely have to stick.
They really do. Those tolerances, the safety limits, the emergency action steps, these aren't just abstract test questions. They are the safety net that protects patients and staff from harm in the real world.
Precisely. And that's why coming back periodically to review and truly understand the why behind these sometimes seemingly dry QA points and regulations is so crucial, especially as you move through residency and into independent practice. It's not just about checking boxes on a form. It's about building and maintaining a robust culture of safety within the department.
Well said. It's about vigilance and understanding.
Okay, so to quickly summarize this deep dive into brachytherapy QA safety and regulations, we've really highlighted the unique risks inherent in brachytherapy compared to external beam and the absolute necessity of the guiding ALARA principle.
Right. For HDR afterloaders, you need to remember that plus or minus 5% source strength acceptance tolerance upon receipt, and those absolutely critical daily QA checks, especially the plus or minus 1 millimeter source position accuracy tolerance.
For LDR sources, strict inventory control from cradle to grave, ensuring secure storage, and performing initial source verification upon receipt are key QA components.
And for all sealed sources used in brachytherapy, those mandatory periodic wipe tests, typically every 6 months, with that hard limit of less than 0.005 microcuries or 185 becquerels of removable contamination, are completely non-negotiable for ensuring source integrity.
Performing radiation surveys with calibrated meters is essential after HDR, after temporary LDR removal to ensure no sources are left behind, and before release for permanent implants to help confirm compliance with the 5 millisievert total effective dose equivalent limit to others.
And finally, having well-defined, documented, and regularly practiced emergency procedures for scenarios like stuck HDR sources, remember CSN, or lost LDR sources, stop, survey secure, notify RSO, is vital preparedness for dealing safely with the unexpected.
At the end of the day, strict adherence to this meticulous quality assurance, implementing robust safety procedures, and maintaining compliance with all regulations isn't just a burden or a hurdle to overcome. It's the fundamental, non-negotiable foundation upon which any safe and effective brachytherapy program is built.
It protects patients, it protects staff, and it protects your facility's license and reputation. Understanding and rigorously implementing these principles is absolutely paramount for anyone involved in practicing radiation oncology and medical physics.
Definitely. So here's a thought to leave you with. Given the increasing complexity we see in some modern brachytherapy techniques like MRI-guided implants or highly conformal HDR plans, and knowing the severe consequences that can arise from even seemingly minor errors, what are your thoughts on how future technology or perhaps advancements in QA methods might help further reduce the reliance on human vigilance while still maintaining the necessary flexibility for treating diverse and challenging clinical situations? Something to ponder.
That's a great question for the future. How do we make safety even more robust?
Complete practice oral boards at RadOncSmartLearn.com and subscribe to RadOnc Smart Review for our next deep dive. Thanks for tuning in.
Thanks, everyone. Stay safe out there.